SAS demonstration video graphing. The dataset used for this demonstration is the same dataset that was used for the demonstration on descriptive statistics. It's the treatment of mild hypertension dataset, and we're reading in just selected variables from 100 randomly selected participants in the study. I've also created a variable BMI from weight and height, and I set up a format statement for gender. We will start by looking at the plots that are automatically produced by proc univariate. With the plot statement that's used as an option, proc univariate produces text-based graphics, box plot, stem and leaf, and a normal QQ plot. So let's first take a look at the plots that are just automatically generated from the plot statement. Here are the plots that automatically come with the plot statement. As you see, proc univariate does produce a lot of output, and at the very bottom, the last page of output is their plots that look at whether your variable might be normally distributed. So here we're shown a stem and leaf plot, we're shown a box plot, and we're shown a normal probability plot. And if we look at this stem and leaf plot for the variable BMI, we see that it appears that the distribution is bimodal with 2 peaks. So it does not look like the data is totally normally distributed. Proc univariate can also be used to produce high-resolution graphs. The output goes to a graphics window. In the following code, we're going to use a histogram to produce a high-resolution histogram, and the probe plot statement creates a high-resolution normal probability plot. The inset statement inserts summary statistics as part of the plot. So here we've modified this proc univariate code. Note here that before I've started the code for proc univariate, I've included this statement, G options reset equals all. I tend to do this whenever I'm running any procedure that produces plots because it basically resets the graphics options to their default options and cancels any global and note statements definitions. So let's say I had changed the font or had made the height of titles or the color of the lines in the graph a certain specification for one particular plot, and in the next plot that I'm doing I don't want those specifications. The G options reset equals all clears out any of those changes I've made to the default options, and you're back where you started from with the default options for graphing. And we'll see later on how I do change some of these options to make the graphs look different. The other thing I wanted to mention before we go over the code is that the way I've set up the preferences on my PC SAS, I do not have ODS graphics turned on. So I want all of my output just to go to a separate graphics window. And again, there's a demonstration video from the first week of the course that talks about how you can change the options on your PC SAS so you don't have ODS graphics turned on. And I think it's particularly important that you make sure your options for ODS graphics are turned off while you're doing these kind of graphs that I'm demonstrating today. So let's get back to proc univariate. So here again we're looking at the variable BMI, and we're asking to do a histogram of BMI, and I've even set up the option to create my own midpoints for each of the bars in the histograms. So the midpoint option has BMI values grouped so that the midpoint of the bars are at 20, 22, 24, and then the last bar has a midpoint of 40. Also, I want to inset a statement block that shows some simple descriptive summary statistics inside my plot. I've given the plot a label for BMI. So I've actually, rather than have BMI appear on the plot, I'm going to have body mass index appear on the plot. Then within proc univariate, I've also requested a normal probability plot with the probe plot statement. And so I have a title for histogram and normal plot of BMI. So let's take a look at what this code produces. And we're going to go to the graphing window. So it says graph 1. And the first plot you see is this histogram of BMI. And notice here that I have this inset box that I wanted in the northwest corner, summary statistics of BMI. Notice here that BMI comes out with a nice label, body mass index. I also asked in my code that a normal probability curve, a bell curve, be fitted to the plot. And I'll again remind you where I did that. So here is our histogram of BMI. Again, it looks a lot nicer than the text-based graphics that you saw that were produced when we just had the plot statement with proc univariate. Now if I scroll down, here's the normal probability plot of BMI. Again, you see a much nicer plot than you did when you just used the plot statement in proc univariate. So again, let's just go over the code here. To do a histogram of BMI, the normal statement said to plot a normal curve, and that's what we saw in our plot. We wanted our inset in the northwest corner, so the position equals NW. So we wanted the little box to appear in the northwest corner. And we had a little header for it, summary statistics. With the probe plot statement, we created a probability plot. Normal creates a normal probability plot and is the default, but you could have created other probability plots for other probability distributions. By specifying mu equals EST and sigma equals est with the normal option, it requests a reference line corresponding to the normal distribution with the mean and standard deviation estimated from the sample. So let's once more look at the plots that were just created. Here is our normal probability plot, and if I scroll back up, here is our histogram with our summary statistics in the northwest corner of the plot. Proc G-chart allows us to create bar charts. Once again, I had the G options reset equals all so that I cancel any of the specifications I made from my proc univariate code. I'm now interested in looking at the frequency of observations from each clinic that participated in the study. So I want to know how many participants there were in each clinic in the study. Here we have proc G-chart, V-bar clinic. So we want a vertical bar chart of clinical center. Frequency is going to be the default for the height of the bars. So let's run this and see what happens. So here we have a vertical bar chart of clinic center. And so it's telling us the number of participants from each clinic center. So the frequency here is our height of the bars, and there are 4 different clinics that were participating. From Clinic A, we have about 18 participants. You can also request to have horizontal bars instead of a vertical bar chart. And the other thing I'm doing with this code is I'm changing, instead of having the length of the bars represent the frequency, I'm now requesting percent. So what percent of participants are from each clinic center? So let's see what happens when we look at this code. And again, we scroll down. SAS always appends its output to the bottom of the window. And here, when we request a horizontal bar chart, notice we get some additional information that we didn't get before. It automatically, by default, shows us the frequency, the cumulative frequency, the percentage, and the cumulative percent. So it looks like the output you would see if you had done a proc freak tables clinic. It just automatically generates that when you request a horizontal bar chart. And notice here that our x-axis is percent rather than when we saw the vertical bar chart with frequency being the default. Now let's say we wanted to make this bar chart a little bit more attractive. So we want to add some labels and some axes so that it appears a little bit more attractive for display purposes. So the first thing I'm going to do is I'm going to give a label percentage of participants. I want to rotate clinical center so it appears along the y-axis and looks aligned with the y-axis. I've also given a title, and in order to attach these axis options to my bar chart, I am saying H bar clinic, just like I did above, and then I'm saying that the R axis, which is the definition of the axis for the response variable, is going to equal axis 1. The M axis, which is the axis definition for the Y axis, is going to be axis 2, or clinical center. So our y-axis is going to have the label clinical center, and our x-axis is going to have the label percentage of participants. So let's take a look at how these changes have enhanced our plot. So now notice, by rotating 90 degrees, clinical center appears aligned along the y-axis. And here's our label for percentage of participants. Let's compare this to the previous plot. Notice here we just have clinic right up on top and percent. And that's just the default label because we had said type equals percent. So again, this plot just looks a lot more attractive. That was done by adding these axis options. Besides requesting frequencies and percentages for categorical variables, you can also do a bar chart with continuous variables, and you can have the height of the bar be either the mean or the sum. And this is done with the sum var option. So using the sum var option, the following code creates a bar chart with the height of the bars equal to the average cholesterol level of participants from each clinical center. So here we have V bar clinic, and the variable for the height of the bars is going to be baseline cholesterol, with the height being their mean value. So we have the mean cholesterol level by clinical center. Again, I'm going to scroll down to see the output, and here we see a vertical bar chart, the mean cholesterol by clinical center. So each of these bars, the height of them is the mean cholesterol level at baseline of the participants from that particular center. We can enhance this plot by also requesting to have error bars placed on the plot. So the following creates a bar chart with the height of the bars equal to the average cholesterol for each clinical center, and includes error bars representing the 95% confidence intervals. So now we're showing this exact same plot, and we've added error bars, 95% confidence interval error bars. So here we see the same bar chart, vertical bar chart with error bars. And once again, we could go back and make an enhanced version of this bar chart. We could have an axis statement and rotate cholesterol baseline as we did before. We could give a proper label to clinic. So again, you could make this plot much more attractive by adding more features to it. Proc box plot is used to assess the association of a categorical and continuous variable. You need to sort your data before running proc box plot. So you need to first sort the data by the categorical variable. In this case, we are interested in looking at the association of baseline cholesterol and clinic. So we want to produce a side-by-side box plot of baseline cholesterol and clinic. Clinic here is our categorical variable. So first we're sorting our data by clinic, and then we write our proc box plot. So we have a title statement, box plot for continuous and categorical variable. And notice that the first variable is our y-axis variable, and it's our continuous variable, cholesterol baseline. And then the second variable is our categorical variable, and it's our x-axis variable. Once again, I have this G options reset equals all so that I have the default options in place. So let's see what happens when we run all of this code for proc box plot. And here is our side-by-side box plot. So notice our y-axis is baseline cholesterol, our x-axis is clinic. And here we have, for each box plot, we have the plus sign, which represents the mean. The straight horizontal line represents the median. The bottom and top of the boxes represent the 25th and 75th percentiles, and the lines extend out to the maximum and minimum values. Proc-G-plot is used to produce scatter plots and can assess the association of two continuous variables. So here we are looking at producing a scatter plot of BMI and age. When you have the plot statement in Proc-G-plot, BMI is going to be on the y-axis and age will represent the x-axis. I've also included a new statement, the where statement, and what I'm asking for in this plot is I only want to do a scatter plot of BMI and age where gender equals 2 or gender equals female. So we want to do a plot of BMI and age for women. And the where statement is a very useful statement to use in procedures when you want to select out just a specific group. And so you can use this where statement in any of the statistical or graphing procedures. So let's see what our scatter plot looks like. So here we have a plot of BMI and age for women only. We have BMI on the y-axis and age on the x-axis. Now let's do some different things with this plot. So now we're going to specify a plotting symbol. In the first plot, we just went with the default options. Now we're going to specify that we want our plotting symbol to be a dot that's black. And we do this with a symbol statement. So we have this symbol 1, color equals black, value equals dot. And then we have the exact same code, and this symbol statement is going to now be in place for this particular plot. So here we have the exact same plot as we did before. This was the default options with these little pluses, blue pluses. And here we see it where we specified a plotting symbol of a black dot. So here you can see more clearly that there appears to be an association between age and BMI for women with the black dots. It appears like it's a negative association, that BMI goes down as a woman's age goes up based on our particular study sample. Let's say we wanted everybody on the graph, so we want to do BMI and age. Look at the association of BMI and age for everybody who participated in the treatment of mild hypertension study, the data that we have. But we want to show different plotting symbols in terms of whether you're male or female. So we have BMI star age equals sex. So then the dots for males are a different color than for females. I've reset all the options, so we're going to be back to the default options, and let's see what the plot looks like. So here we see our default plotting symbol of a plus. Red pluses represent females, blue pluses represent males. So here we have a plot of age and BMI for everybody in the study. Now the next thing that we're interested in is adding regression lines by gender. So we want to have two regression lines on our scatter plot. A regression line for the association of age and BMI for males, and a separate regression line for the association of age and BMI for females. So we have to add quite a few statements to produce this kind of plot. Here we have two symbol statements. Symbol 1, and the 1 means to assign the options that follow to the first sorted variable name that is to be plotted. So symbol 1 is going to be attached to males. And we want for males the value of the points, or how the points are going to appear, are as stars that are black. And then we want to add an interpolation of a regression line. RL equals a regression line. And we want the line to equal 1. We want a solid black regression line. For females, symbol 2, we want the points on the plot to be circles that are red. We also want an interpolation line for females. So we're asking for an interpolation equal to RL for a regression line. And line equals 2. Now the line option, line equals 1, is a solid line. If you set line equal to 2, anywhere up to 46, SAS is going to produce some kind of dashed line. The option interpol actually means interpolation. So we could have requested other kinds of interpolation lines to be placed on this graph. But for now, I'm going to show you how SAS uses this option and places a regression line on the graph. Before I run the code, I also want to point out that I've created two axis statements. The first one, axis 1, I want to attach to the vertical axis, and I want body mass index rotated 90 degrees, so it's along the vertical axis. I've given it a font and a height. For my x-axis, I've given the label age in years and a font and a height. So let's run all of this code and now see what the plot looks like. Pretty nice looking, huh? We have linear regression lines for gender. Males are shown with black stars. Females are identified with red zeros or little red circles. We have a dashed regression line for females in red and a black solid line regression line for males. Just looking at the plot, you can see that there appears to be a stronger association between age and body mass index for females than for males. And here we have our key telling us that the black solid line with the stars are males. The red dashed line with the little circles are females. Also notice that the body mass index label appears aligned with the vertical axis, and the label age in years is along the x-axis. And in the code, to make sure that the horizontal axis goes along with the axis 2 label, you have these options that after a slash with the plot statement, h-axis equals axis 2, v-axis equals axis 1. Gplot can also be used to produce a plot of the means and error bars. And this is a common thing to do if you want to look at the change in a certain continuous variable over time. So if you wanted to look at how mean cholesterol levels changed over a time period where it was measured at baseline, at 3 months, 6 months, 9 months, 1 year, a plot of means and error bars can be very helpful to look at that. And you would use procgplot to produce a plot like that. So let's look at the code. I'm doing a plot of the mean cholesterol level and clinic. So I'm starting out by resetting all of my options to the default. And then, again, I'm making use of the symbol statement. And so when I want to do a plot of means and error bars, I don't want all of the dots on the plot. So it's not going to look like a scatter plot. So I'm saying that I don't want all the individual points put on the plot. So I've set value equal to none. For my interpolation, I'm asking for 1 standard deviation error bar. So 1 STD 1 standard deviation. The J connects the means from bar to bar with a line, and the T adds tops and bottoms to each line. Again, the value equals none option suppresses the graph of individual points. Line equals 1, we request that a solid line connect the mean BMI values. And then at each point, at each clinic, you will see standard deviation bars. So in our procgplot, we're plotting baseline cholesterol, that's going to be our y-axis variable. Clinic is our x-axis variable. The horizontal axis, which is our x-axis, is going to have the label clinic. The vertical axis, or y-axis, is going to have the label baseline cholesterol, and it's going to be rotated 90 degrees. The offset equals 5 starts the plot about 5 units over. So let's take a look at all this and see how these options and symbol statement produce a plot of means and error bars. Here we have baseline cholesterol level as our y-axis. At each clinic center, we have a point here where the line is, that's the mean cholesterol level, and these are the 1 standard deviation error bars. So at clinic B, here is the mean cholesterol level and the 1 standard deviation error bars. At clinic C, we also have that, and at clinic D. the line equals 1 creates a solid black line that connects the mean level of cholesterol at each of the clinics. So this is a plot of the means and 1 standard deviation error bars. A similar kind of plot that's used often is a plot of the mean and error bars where the error bars are 2 standard errors or 95% confidence interval. So the code here for this type of plot is very similar to the code I just showed you before. The only difference is with the interpolation statement. So here I'm requesting, instead of 1 standard deviation, I'm requesting a 2 standard deviation of the means. So here we want the standard deviation of the mean, which is the standard error, and we want the plot to show bars that are 2 standard deviation of the means joined with a top and a bottom. So we have the J for joining those top and bottom values and having tops placed on the bars. So the only difference in this plot that I'm showing here is that the error bars represent the 95% confidence interval. So here we see the exact same plot, but at each of these clinic centers, we now have the mean baseline cholesterol level and the 95% confidence intervals put on our plot. And then we've connected these mean levels with a solid line. And so notice how it's different from the plot above where we plotted 1 standard deviation error bars. Here, in this new example, we are showing the plot of the means with the 95% confidence interval bars. So I've gone over a number of different plotting procedures. I've shown proc univariate and proc G-chart. Proc univariate produces histograms and normal probability plots. Proc G-chart can be used for bar charts or histograms. We looked at proc box plot to produce side-by-side box plots. And then we finally looked at G-plot, which can produce scatter plots. It can show regression lines or other types of lines fitted to the plots, as well as G-plot can be used not just for scatter plots, but to produce a plot similar to what I just showed you with the means and error bars. This completes this demonstration.